Hi, my name is Davide Mottin, and I will present SOFOS, demonstrating the challenges of materialized view selection on knowledge graphs. This is a joint work between myself, Georgia Trollinou, Haridimos Kondilakis from Ford, and Matteo Lisandrini from Aalborg University. Knowledge graphs lie at the core of a lot of technology. More recently, smart assistants. In smart assistants, you can pose questions and then you get an answer like, what is the capital of Denmark? A knowledge graph is basically a graph where nodes are specific entities like Denmark or Copenhagen. And relationships have a specific semantic meaning, so like is capital of. So each of these edges are called facts. Nowadays, we have several of these knowledge graphs, and they're used in many different disciplines, from medicine to fact-checking to normal queries and question answering. They are growing in size, and nowadays we also have quite a few databases, specialized databases that store these graphs, and you can actually perform some queries. One of the models for knowledge graphs is the RDF model. And there are several RDF graph databases that can actually serve specific queries like SparkQL queries. In particular, for this kind of graphs, one sort of queries are analytical queries. When you ask, for instance, some questions about the statistics of the nodes or some characteristics. For instance, Denmark can be associated to the population, and the population size is a number. Then you can ask what is the average population in Europe of the countries in Europe. All these questions are analytical questions. The counterpart of these analytical questions are the OLAP queries in the relational database. Typically, these questions, since they require to traverse the structure and then ask and aggregate, are very, very time consuming. And most of the RDF data management systems are actually slow in answering these kind of queries. One solution to this problem is view materialization. View materialization is the solution that you will have a query, and for a query you have a materialized version of these queries. That means that the results are stored. This technique has been used extensively in graph databases. In data cubes, this is one of the main techniques for speeding up queries in general. Materializing a view doesn't mean only to speed up the single query that you are materializing. It means also that you can do some smart algorithmic compressions and have answers to more refined of the queries. So it's actually a very, very common technique. This is, as I said, very, very studied in a relational database, and the requirements. So one of the main ingredients here is a cost model. And the cost model is telling you which view do you want to materialize? What is the most convenient view to materialize? And this is not an easy question, because you cannot materialize all the possible views because they are exponential, and the space, the storage, is limited. So which view is better than the other? Although this is extensively studied in relational databases, for knowledge graphs, this is not the case. There is not a solid consensus on what is actually the best practices to construct view or to perform view materialization in knowledge graphs. There are a few sparse studies, but none of them are actually telling you exactly what are the drawbacks or what are the differences of considering the RDF model as opposed to the relational model. The problem is that an RDF typically doesn't really have a schema, which is heavily used in the case of relational data to simplify, to make every query faster. So then there are, not having a schema means that you have also nodes that are blank, so that they might not have a specific value. There are very complex relationships among objects. So it doesn't seem as an easy question. And this is what we would like to answer. So the demonstration scenario that we are going to propose today, SOFOS, is actually answering some of the questions like, can we adapt techniques from the relational model to the knowledge graph world? Is there an optimal cost model for any use? And what are actually the pitfalls? So what is better in one cost model with respect to another? So SOFOS is this kind of demonstration. So it is an application that allows you to compare and evaluate different cost models for view selection. It has been adapted to RDF. So not all the possible cost models were existing, but we have made some adaptations for the specific RDF case, and also for materialized in the view, and we will see that later. SOFOS allows you to run a sequence of queries and compare the different cost models immediately. And therefore, you can inspect the performance, you can modify the query, you can understand which factors are penalizing or making advantages for some specific cost model. And we can identify somehow in this way the strengths and the limitations of the models that are proposed in the relational world. How does the SOFOS workflow work? So what will you see in the demonstration scenario? Well, you start with an analytical facet. And what is an analytical facet? Is basically a definition of which nodes entities are you interested in. So you focus in some specific area. In a relational database, you might be interested in some specific tables. In SOFOS, in the RDF world, you might be interested in some specific area. It is basically the definition of a template for multiple different queries. And it tells you, okay, a set of variables, a set of predicates, which is basically edges, or so somehow constraints on edges, and an aggregate function, so which could be count, which could be average, which can be mean, max, and so on and so forth. This is the input, so which is resembles in that form, and then you're given in input a specific cost model. The output is what is the storage cost if I consider this specific cost model, and what is the query response times if I pick that cost model, I materialize the views following that cost model, and I run some queries. So in a more simplified manner, this is what happens. So you have an offline module in which you give it as an input a facet and a cost function. Using that cost function, you have an offline view selection and view materialization that happens before, right? So it's like constructing an index. Then on the online part, you can basically either just look at the lattice of all the possible views, because it's a lattice, right? So it's all the possible filtering and all the possible projections that you have over your query. You can send the query, record the time, getting the results, and then evaluate yet another cost model. So in the backend, you basically have a knowledge graph, which is stored in a virtuoso environment, but it can be stored in any other FDF model. This is not a constraint. It's there is basically a database in the back. Just to give you a more simplified view of what a facet is, well, a facet is, as I said, a group of variables like population, federation, and state, and it is identifies a portion of the graphs in which you have states, and each state has population details, has a name, has a language, and is part of a larger federation, for instance. You define an aggregate or a sequence of aggregates, for instance, the count over the state. Then you have a set of predicates that tells you, okay, how you should relate, how the queries, the queries that you are going to answer will relate somehow, or which kind of relationships they will have. And here is, for instance, a query that belongs to that specific template. So in which we have group by language, and we return French and Italian and the count of how many states speak French. So far so good. And what are the cost functions that we have evaluated? Well, we start from the simple one, the random one, and this is basically constant for each view, so you don't have a proper cost because it is indifferent over the set of views that you have in front of you. Then you have the number of triples, which corresponds to the relational number of tuples, and you basically count how many triples do you need to consider to construct that view. So how many triples this view will have. Same is also the number of aggregate values, that is the number of results of the specific queries that represents the view. And this is basically the number of aggregates. So in the table before it was 3 and 1, so 2. The number of nodes is basically the number of single values, because for each value, remember that we need to create somehow in an RDF word that represents a node, and therefore we are counting the number of nodes. And what if we want to minimize somehow? What if we have a minimum cost in the number of nodes? We also introduced something different, which is a learn cost. And I want to spend a bit of time here because I think it's an interesting thing. We have done a very simple thing. So we have represented the query, which represents also a view, as a vector. And this vector roughly represents some characteristics over that view. Therefore, it is not bound to the specific data. It is bound to, if you want, the learn cost is bound to the database, more to the data. Why it is bound to the data? Because what we do in the train phase is that we generate pairs of views, and we compare somehow the benefit. So we return a value. So we generate a lot of these pairs, and we return a value which is what is the gain that we have by considering a specific view, more than before, basically more than executing the query just simply. So this is what we have in the test phase. We can basically return for each pairs of views, we can return a benefit. The last one is a user-defined function in which it's basically a game. So we will ask you, okay, given the lattice of all the possible views, because you have this exponential number of views, click on the views that you want, select those that you think is reasonable, and then let us run some queries. If you're lucky or if you're good, you should be better than the computer in selecting the right view. If not, well, your time will be lower. The step before executing queries is view materialization. Here we follow a standard procedure, but you have to consider that for each aggregate we need to create a specific node that represents the aggregate, right? So if the number of countries that speak French are 3, then 3 has to be stored in a specific node. So because everything is stored inside the database, it is a materialization in the end of the day. This is very, very similar to what has been done previously in a work called Marvel from 2016. In the end, and this is what I will leave you now to play or to see how the demo works. You will see this kind of interface in which you will have the full lattice, so all the possible materialized views that you can pick up. You can select the different cost function, and if you select a specific cost function, you will see the time for executing a specific query. So here you can also play with, okay, I want to perform this query instead, and see how the time changes for different cost functions. So that's it. I hope you will virtually stop at our booth, and you will enjoy now the demo, the demonstration that we will show. Okay, thank you very much.
Thank you for being here. So I am going to demonstrate to you how we use SOFOS to understand view materialization for RDF knowledge graphs. So in SOFOS, we have different datasets here. Now we're going to use the LUBM one. For this dataset, we have prepared a number of templates. These provide different analytical views over our graph. We can select now one of them. Here we see the query that will generate the base data that we want to aggregate. So this is the view with all the facets that we want to understand. So students, faculty, which actually is a teacher in the LUBM dataset, course, and universities, and how they are connected. Now we select a budget, that this will be how much space we want to dedicate to our materialized views. To ease of understanding, we, as a space unit, we use the number of triples. So here I'm putting this budget. And we can proceed now with testing different materializations. Here we see the lattice. At the base, there are the facets that we want to analyze based on our query template. And here are all the possible aggregated views that we can build on top of it. Each one has a different size, again, in number of triples. If we are going to compare this to the total graph, here we see the full number. And if we materialize all the views, that will be the number of triples that will be required. On the right, we have different cost functions we can select. A simple example could be number of triples. So what will be the lattice that we are going to select if we use as a cost function the number of triples in each view within the budget? Here is the lattice. So we see that only few of the possible views can be materialized given our initial budget. Then we can test the performance of this given some query. Here we have prepared, for example, queries for this demo. So in this query, for instance, we are going to count students within the university. We can now execute the selected query, and now the system is going to execute it first on the original graph, so without any view materialization, and then it's going to execute it given the best view that we can select among those that we have materialized with our cost model. Here we see the running time. As we see, aggregating the number of students per university on the original graph will require 4 seconds. Instead, the same query, when we have materialized the view, will require approximately 17 milliseconds. Now, this is with the number of triples. So given these available views, if you select a different cost function, in this case, number of aggregated values, we can see a different selection. In particular, we notice that in this case, we are selecting an aggregated view that actually aggregates across universities. This will be perfect for the query we are running. So now we can test the same query in this set of materialized views. And of course, the system is going to pick the best view, so the view where we aggregate per university, to answer this specific query. Let's see the time that it takes now. And here we have, given this appropriate materialized view, the query will take only 3 seconds in this case. We can test different queries and try again the running time based on the specific views that have been selected. The query we are running here now aggregates students per course and university. And we see we don't have the specific materialized view, for instance, in this case. So we will need to compute it from a lower materialized view, which will be a bit less performant. And here we see that in this case, it takes almost 100 milliseconds instead.